Hello and welcome. This is chapter number 11, AC power analysis of our Sadiku's textbook. In this lecture, we'll be talking about power factor correction. So what exactly our textbook tells us about the power factor correction? So for power factor correction, it is the process for increasing the power factor without altering the voltage or current to an original load, or alternatively, the power factor correction may be viewed as the addition of reactive element, usually a capacitor, in parallel with a load in order to make power factor close to unity. The reason for connecting a capacitor as a reactive element usually is because generally our loads are inductive in nature. An inductive load is modeled as a series combination of an inductor and a resistor. So for example, this is our load or an inductive load. This is how an inductive load will look like. This will be the resistor and this will be the inductor. So this load will have some power or will have useful power absorbed across this resistor. That will be the P, and there will be some reactive power that will be absorbed, or you can say associated with this inductor. And that basically a reactive power is basically that goes in this inductor is basically that oscillates from between the source and the load. So what is happening over here is that we actually need a power that is equal to S in order to support such a load. The useful power is P, whereas Q is the power that is not used in any useful work. So how we compensate this? We compensate this by adding a minus Q to this whole system. And that thing, or that is done by adding a capacitor or a capacitive load in parallel to this, or this is XC, or in parallel to this load, a capacitor is added. So overall what happens? This S becomes P plus JQ dash, and this Q dash is less than Q actual. And this eventually gives us a benefit that when we add a capacitor, the Q component or the reactive power component decreases, and hence the value of S that is required, or the power that is, or a complex power that is required to support this load, that is decreased. And in actual power systems, this is the size of our generators. And in the end, I will talk about this thing in a little, in an example to show you how or what are the effects of this thing on a big power system, or what are the benefits or what are the advantages we get by using or this concept of power factor correction. Similarly, we can see that we have a power triangle. We have seen this in our last lectures. We have power across the x-axis. We have the Q, or the reactive power component, is orthogonal to the uh, you can say useful power in watts, which is over there. Remember, the units is for power are watts, and the units for Q are VAR, volt ampere reactive, and the units for S are VA. Similarly, power is proportional to the resistive component of our load. Q, or the reactive power, is proportional to the reactive component of the load, and S, or the complex power, is proportional to the overall impedance of our load. We have also seen that if our load is capacitive in nature, the, the Q capacitance, so the Q will be negative and the power triangle will be on in this lower half plane. And similarly, if our Q is positive, or means that we have inductor or an inductive load, our Q will be positive or the power factor will be lagging. And we have seen this thing in detail in our previous lecture. So remember the overall process of increasing the power factor without altering the voltage or current to the original load is known as power factor correction. So I mean, in my last diagram on my last slide, I have drawn the same circuit which is drawn over here. So here we see that we have a voltage that is appearing across a load, and that load is inductive in nature. It has some XL and some R. So overall Z equals to R plus JXL. So there is some current I that is flowing. Similarly, if we add a capacitive component, a capacitor to this load, so overall the impedance, or there will be some decrease in this effective reactive component of this impedance, and that basically is or can be seen from here. So if we have a overall effective load IL going here, the load or the current through the capacitor will be something like this, or that current basically through only through the capacitor will be 90-degree out of phase, or leading 90-degree leading in a capacitor only. So this is IC capacitor only, capacitor only. And if we use the triangular or the parallelogram law for vector addition, we can have these parallelograms, or we can have these vectors added together, and eventually our effective current I, which is drawn from the source, becomes something like this, and this angle, and the angle for this is phi 2. And if I'm going to measure the cos of phi 2 for this angle and cos of phi 1, so cos theta, remember, is our power factor, and this is my initial power factor. So my PF power factor is greater than PF, oh sorry, PF dash is greater than PF in that case. So that is what we call it as power factor improvement. And eventually what happens, the amount of current that is drawn from the source decreases. So if the amount of current drawn from the source decreases, so we multiply by I conjugate, so the overall complex power will also decrease. So I am also, remember, I am also assuming that these values are in RMS. So let's draw, or if we have to draw a power triangle for this thing. So for this part A, my power triangle will look something like this. My power will be the useful power across R will look something like this, and my power that is not used, or my overall uh, value of power across you can say this inductive load is something sorry, something given as Q1, Q1, and my overall effective power will be S. So what happens when we add a capacitor? So if we add a capacitor, my overall power remains same. The useful power, the resistive component, remains the same. Remember, my Q1 will be in this direction, and my Q, because of capacitor, will be in this direction. Q circuit for such a case will be P. So Q1 minus QC will, you can say something like this. So this is Q1 minus QC. So eventually my power S will be something like this S dash. So this is what they are saying over in this diagram. So this is, for example, S1. So this is my S2. So this is my new Q2, and this Q2 is actually Q1 minus QC. That is because of this capacitor. So let's see this diagram in detail. So looking at this diagram, if I'm going to find out the sorry, the value of Q2. So remember, this value of Q2 can be found out by by what? For example, if we have this O, A, B, C. So this is my the triangle, and this is a, remember, a right angle triangle. So we can just use the sine and cosine angle and tangent angles, or all these angles for this right angle triangle over here. So for Q2, remember Q2 is or the tangent of theta 2 angle of theta 2 will be q2 over p. So my value of q2 will be p times tangent of theta 2. Generally, this power is given to us. Uh, so this is my q2, and if we have to find out the value of capacitor, so required, or we know the initial value of q1 and the associated power factor. Okay, so we know the power factor and the associated q, and we know the power factor which we have to improve, and the associated you can say q2, and the change in q. So delta q will be uh, q1 minus q2, and this is the delta q is provided by the capacitor or the qc which we have. So and if we have to find out the value of capacitance, so remember xc equals to 1 by j omega c. So xc is 1 by j omega c, and we also know that we you can say mm, v equals to I times z, and for a capacitor, I times a capacitor multiplied by impedance of a capacitor. So voltage of a capacitor equals to IC. Impedance of a capacitor is 1 by j omega c. So if we have to find out the value, or so from for him here, we can easily calculate IC as VC times j omega c. So this is the value of I, and this is the value of V. So if we are going to use both formulas, so my overall QC, the power will be, uh, you can call it VI, or I square R, it's up to use, or I square R, or V square by, not R, you can call it ZC. So any of these formulas can be fine. So we have both value of IC and VC. So I use this value, and I've used a little different formula so that you may be able to see the values yourself as well. So QC becomes equal to uh, VC multiply by VC j omega c, and QC becomes equal to JVC square omega times c. So if I have to calculate the capacitance, we just have to, use the magnitude QC divided by VC square into omega. And this is what exactly QC VC square by omega, or remember these values are calculated in RMS. And for QC, we know that this Q value of QC can be calculated as this, or Q1 minus Q2, and putting these values in the formula, we can easily find out the capacitance that is required to improve the power factor of a load. So let's see, again, this is the same thing. So, so let's see an example. uh, uh, so before, I mean, I go over there to an example. So here they are basically talking about that what happens if if our load is capacitive and we have to um, improve the power factor. So in case our load is capacitive, in that case we have to add a shunt inductance. Remember, a shunt inductance or an inductance in parallel to the load. And in that case, again, similar situation happens. Q1 minus Q2 will be again P tan theta 1, PT tan theta 2, and the values will be the same. Just this value or capacitance will be, so we have C equals to V square over omega QL. The only difference is uh, uh, that this relationship is inversed, because impedance Z omega, it will be J omega L, and we have ZC as 1 by J omega C, and that has basically done what that it has reversed this relationship. So let's solve an example and see how this thing can be done. So we have this is the example 11.15 of our textbook. It says that when connected to a 120 volt RMS 60 hertz power line, the load absorbs 4 kilowatt. So for example, this is your load. This is your load, and this is absorbing 4 kilowatt at zero point 0.8 power factor lag. The voltage that is applied is 120 volt RMS, and frequency is 60 hertz. Okay, find the value of capacitance necessary. So now the power factor 2 that is required, that is 0.95 lag. This is the power factor that is required. This is the power factor that is actually we have. So let's draw first case, draw the power triangle in this case. So for power triangle, if we draw the power triangle, we have P over here, and we have Q over here, and we have S over here. So we have Q, so I call it as P1, this is Q1, and this is S1. So this will be my angle theta1. Okay, so let's calculate this value. So P1, remember P1 is 4 kilowatts. Cos of theta1 is 0.8, so theta1 becomes 36.87. Yes, so theta1 becomes 36.87 degrees. We have theta1. So we have this angle. This is 4 kilowatts. This angle theta1 we have. So we can easily find Q1. Q1 is P times tangent or P1 times tangent of theta1. So if we multiply it, so my Q1 value becomes or comes out to be 3 kilo. So it comes out to be 3 kVAR. So 3 kilo VA volt ampere reactive. So similarly, the value of S1, if we have to calculate, it can be either P square plus Q square whole under root. So it will be 5 kVA. Okay, so this is my value of S1. So I have now S1, I have Q1 as 3 kVA, kVAR, and S1 is equal to 5 kVA. So we have these three values. So now what we have to improve? So we have to improve the power factor to so improve power factor 2 is 0.95. It means that cosine of theta2 or the improved power factor is 0.95, and the theta is cos inverse of 0.95, and that comes out to be 18.19 approximately. Yes, so 18.19 degrees. We have this is our new angle. So what will happen over here? So the new power triangle. So new power triangle. So the new power triangle, remember the active power or useful power will remain the same. So P will remain the same. So P1 will be 4 kilowatts. And now theta2 is basically 18 degrees. So this is now theta2. This is 18 degrees. This is Q2, and this is my S2. So now find out the value. So remember S2. So first find Q2. Let me. So the value of Q2 will be P2 tangent of theta2. Sorry, P1. It remains the same, P1 theta2. So my value of Q2 will become 1.313 or 1.3144 kilowatt reactive. So now I have the value of Q. So S will be S2 will be P2 P square plus Q2 square whole under root. So if I have having this value is this 1.3144 VAR, squaring both and taking the under root, my S value will be 4.2105 kVA. So this is my S2. So my S2 value will be something like this. So now we have to find this value of capacitance. So remember, my Q1 was 3 kVAR, and my Q2, or after the improvement of power factor, my Q2 was 1.3144 kVAR. So the delta Q is what that is supplied by the capacitance, or QC. So that QC will be Q1 minus Q2. So if I'm going to subtract these two values, I get around 1.6856 kVAR. So if I'm going to subtract both values, so my effective Q becomes something like this. So now this is the value of Q, or this is the power that has been, or the reactive power that has been supplied by adding a capacitor in parallel to our load. So remember the capacitance, how we calculated the capacitance, or QC. QC is reactive power. Reactive power is VC times IC, or it can be calculated as VC square by ZC, or Z impedance, or uh, IC square times ZC. So any of these formulas, this thing will give you omega C V RMS square. So QC again, let's put in the value 1.6856 kilo. Again, omega is 2 pi f, frequency is 60 hertz. Remember, omega is 2 pi f, frequency is 60 hertz. Multiply capacitance, we have to find out. Our voltage RMS value is 120 square. So from using this value, my capacitance comes out to be something, or it is 1030.5 microfarads. So this is the value of capacitance that I need to get this improvement of power factor over here. So this is how we go with this. Then the question, the very important question from a practical point of view that comes here, is that why power factor correction is important and why it is required. So for example, let's say I give an example, or I'll give two examples to you. For example, say you have a power system and your load is 1 megawatts, and you're operating at power factor of say 0.8. So if you are operating at power factor of 0.8, what will be your power, or what your power factor triangle will look like? So you have 1 megawatts of power that is useful, we call it P, and then there is X amount of, so there is Q2, and say this is your theta and this is S. So Q will be the theta angle is 36.87, and the value of Q from how we calculated earlier is P1 tangent of theta 1. So remember theta, or this is theta 1. So theta 1 is cos inverse of 0.8, and this is 36.87 degrees. This is my theta 1. So just simply tangent of the 7, it comes out to be 75, or this thing will be 0.75 megawatts, and my overall S will be here plus 1 square will be around 1.25 MVA. So this is 0.75 MVAR. So remember, say if this is 1 megawatt of load for an industrial load, or a small village load or something like that, in order to supply this load at this power factor, you need a generator of 1.25 MVA, right? So you need a generator that is able to supply 1.2 megavolt into amperes VA, and out of that, on the power that is supplied by this generator, you are only able to utilize 1 megawatts for the or for useful purposes, but you have also unutilized power, that is 0.75 mega m volt ampere reactive. So this is the amount, this is a huge amount of reactive power that is not utilized. Now, for example, and this generator will cost you say 1.25 million US dollars, for example. Now, if you have improved your power factors for and improved your power factor by adding a load, say for example, improve the power factor to 0.9, so your theta 2 will become, so we can call it as cos inverse of 0.9, and this is 25.841 degrees. So what will be, or what my power triangle will look like, will be something like this. So S2, find out the size of generator that is required if we have something like this. So this is my theta 2. So in that case, what we have is that tangent of, we have this power as 0.484 mega volt ampere reactive. Okay, and the size of my generator that is required over here is 1.11 MVA. So what we have seen here is that if this 1.2 or 1 MVA is $1 million, so this will save me, or this will cost me around $1.1 million. So savings will be 1.25, it will be around $0.14 million. So this is or why we have been able to save this, or even if we are supplying the same amount of load. But what we have done is that we have reduced the power content that is not utilized in useful power by just improving the power factor of the load. And with that, we are able to decrease the size of our generators from 1.25 MVA. We are able to decrease the size of our generator to 1.1 MVA, 1.11 MVA. Or for example, if we can move the power, or even say, just imagine if we are going to move power factor to unity, or unity, what will happen? So for unity power factor, you will have P, and you will have no q equals to 0 for unity power factor, q equals to 0. So it means that whatever the value of P is, your S vector is also the same. So both vectors are same. So P is equal to S. So your generator size is S3 for you is 1 MVA. And that will cost me, say for example, $1 million. So for a purely resistive load, and actually or in practical system, purely resistive loads are not possible, but yes, 0.9 or 0.95 power factors are easily achieved and can be achieved generally with big induction motors and big pumps. The power factor decreases to 0.7, 0.6, 0.75, and in order to improve that, then we use these capacitors or some other devices like synchronous condensers in order to improve that power factor, so that we are able to save the amount or the size, or we have to decrease the size of generator that we need in order to supply this power. And in big power systems, such as on a level of transmission level or a distribution level or on a city level or on a provincial or on a scale of a country, if we are able to save this amount of power for say one locality, and if we map the same to a scale to a huge scale, this power saving can result into billions of dollars, and over the years it can this overall saving by improving power factors can be trillions, and god knows how much you will be able to save in as if by just improving a power factor of your overall load. So this is why we need power factor correction. Also remember that when we are billed or when we are billed for kilowatt hours. So we are built for the useful amount of power we are using. But for the industry, there is another bill that is kilowatt ampere reactive. So this is a penalty that is usually imposed. So if that in because the utility companies measure this reactive power across that industrial units, and if that reactive power is greater or if this power factor is below 0.9 or zero point 0.8 or whatever the standards that country or that place is following, there is a big penalty that is introduced on those or those industrial units. And the reason by of poor power factor for these industrial units is because of these pumps and induction motors and these sort of components which have a big you can say windings attached to it, or a big inductive or a dominant inductive component to them, and that is because of the inherent nature of those devices. So we have to compensate them when we have to operate them. We can't or we can operate them at say zero point 0.6 or 0.87 or zero point 0.8 power factors, but that will severely increase the size of generators which we need to uh, utilize or we need to make in order to run those devices. So again, it's a win-win situation, and that is the reason why we go for as close to unity power factors when we are operating our power systems. So this is for all for this lectures, and in our next lecture we'll start from chapter number 12, that is related to three-phase power systems. Till then, thank you, and thank you for listening.